Hello everyone, in this video we will see memory management in Go. Memory management is a process of managing computer memory, moving processes between main memory and the disk to boost the overall performance of the system. The essential requirement of memory management is to provide ways to allocate memory and when not needed to free them up for subsequent requests. Now programs manage the memory by dividing into two different parts to perform certain tasks. One is stack and second is heap. So stack is a static memory allocation and it follows LIFO, that is last in first out. Stack is used to store function parameters, local variables, etc. Now stack is static and finite, so the capacity of the data should be known at compile time. Since most of the operations in the stack happens at the top, that is pushing and popping, it is fairly simple and fast since there are no need of any lookups and it's all about popping certain things or pushing certain things on top of the memory. Due to a limited capacity, you may sometimes encounter stack overflow error. As compared to stack, heap is dynamic allocation of memory. So in heap, you have the freedom to store n number of data. It is not limited or there is no much capacity, it can be extended, it's very much flexible and you can store, that is you can allocate and deallocate memory anywhere within the heap. So basically in the heap we store pointers, arrays, big data structure, etc. One of the most important concept in heap is contiguous block, which should be large enough to satisfy any request within a single chunk of memory. What it means is, whenever a memory needs to be allocated, the operation must scan the entire heap to find a contiguous block of memory which is large enough to satisfy a request and then return this back to the stack so that the adjacent block, that is the adjacent free blocks, can be coalesced together to accommodate further requests within a single chunk of memory. Due to this, the complexity is high in terms of heap and it is slower than stack. So to summarize, let's say if we have this, you will have this block where you will store global variables, global or static variables. Then you will have stack, which will store function params, local variables, etc. And then you will have heap, which is for dynamic allocation, dynamic mem allocation. So let us see what it means. Most of our modern system is a 64-bit. So we could have a 32-bit or 64-bit. This could be called the word size. So this is basically the size which is used for reading and writing of the data into the memory. Let's take an example. Let's say we have a struct. Let's say we have a struct which is employee. And within that struct we have age, which is unsigned int of 8-bit. Then let's say we have salary, which is int 64. And let's say we have something called accept terms of use, which is boolean. Okay, now this is 8 bit, this is 64 bit, and boolean is 1 byte, that is 8 bit. So if we add this together, this becomes 80 bits. So our understanding would be, this would be 80 bits, that is the capacity, that is the size or the memory used would be 80 bits. But that's not the case, because as we discussed, heap is a contiguous block, and let's say we are in a 64 bit OS, right? Let's try to demonstrate it. Okay, so let's say this is a chunk of memory that we have. Okay, each one going from 0 to 64, just to say that it is 64 bit. Okay, let's say 8, 16, 32, 64. Now age is 8 bit. Okay, so it will take this block. The next field is salary, which is 64 bit, and we cannot fit 64 bit here. Okay, so what happens is it adds 0 padding throughout from the 9th bit to the 64th bit, and the next 64 bit is allocated here. Okay, similarly the next field is boolean, which needs 8 bit, but since we have already occupied 64 bits in this chunk, the 8 bit will go to the next one, that is here, and since there is nothing else, the remaining 56 bits will be padded with 0. So in short, we have consumed 3 passes for these 3 fields, each of 64, 64, 64, which is nothing but 192 bits. So basically our actual size was 80 bits, but we have occupied 192 bits, so we have almost wasted 112 bits of memory. And in order to read our this employee struct, we have utilized 3 passes, right, to read this data. 1 pass, second pass, third pass. Okay, so let us see how we could improve this by just restructuring our bit, by restructuring our struct, okay, such that this combination or the bits use is less, so that we could try to optimize our memory. Okay, so for that what I will do is, let me clean this up. Okay, so what we will do is, let's clean this up and let's see what better we could do. Okay, so we will not do anything fancy. What we will do is, we will just restructure our fields. So since salary is 64 bit int and this is 8, what we will do is, we will just interchange age and salary. Okay, so we will put salary first, which is int 64, and then we will put age, which is uint 8. Now what will happen, we'll see. Again, this is 64 bit, this is 8 bit, this is 8 bit. So this again adds to 80 bits. Now let's see how the memory allocation will be done. So we will draw the same blocks again, each one going from 0 to 64. Let's say 8, 16, 32. Okay, so we'll start from top. So what is happening is, salary is 64, so we have occupied all the 64 bits here. Okay, second is age, which is 8 bit. So age is occupied in the, here age is in the 8 bit. The next is accept, which is a boolean, which is again a 8 bit. Can we fit this 8 bit within the same chunk of memory? Answer is yes. So this will be accept, right? So basically 8 and 8 is 16. So we have remaining 56 bit, which is 48 bit, which is pending, right, which we need to fill it with 0. But in short, what we have done is we have just utilized two passes here, right, just two passes, each of 64 and 64. So instead of 192, we have now utilized 128 bits, and we have saved a lot from our previous where we were occupying 192 bits. Okay, so you see, just by restructuring our fields, we have ensured that we have been taking less memory, as well as we are providing or helping Go to read this chunk of memory struct in just 2 passes as compared to 3 passes in our previous example. Okay, so let us try this out in Visual Studio Code and validate. So what I will do is I will go on to my Visual Studio Code environment. I will create a new file called mem.go. Okay, let's initialize it, and now we have the main method. So what we will do is we will create a struct of employee. Let's have the first case wherein we had age of uint 8 bit. Okay, next we had salary, which was uint, it was int 64. Okay, next was accept, which was boolean. Okay, so let's create and initialize a variable of type employee. So let's call it unoptimized EMP. Okay, employee, and we will assign value, age to be 30, salary to be 10,000, and accept to be true. Okay, so let's print this size. For that we could use printf. Let's give %, let's say capacity of unoptimized employee in bytes. Okay, that is n %d/n, and we will use unsafe dot, it has a method called sizeof, and here we can pass the variable. Okay, so let us run this code, and you see this gives us 24 bytes. So 24 byte is nothing but 24 into 8, that is 192 bits. Okay, so because as you know 8 bits is equal to 1 bytes. Okay, so 24 byte will be 24 into 8 bits, that is 192. Now what we will do is we will restructure this employee and see what will be the response. Okay, so I'll just change the order, and what I will do is I'll make this as optimized employee. Okay, and we will run it. As you can see, now it has occupied 16 bytes as compared to 24 bytes before. So this validates what we just saw in theory on the contiguous blocks, right? So by just restructuring our fields within struct, we could reduce the memory usage, plus we can reduce the number of pass that the system should go through in order to retrieve your set of data. Great, I hope this was useful. That's all I wanted to cover as part of this video. I will see you in the next video. Until then, happy learning.